Thank you very much for coming. It's really great to see everyone in the audience, to see everyone who's interested in virtualization and EC2 instance performance. My name is John Phillips. I've been at Amazon for 4 years now. Spent the entire time in EC2 and in product management with a specific focus on EC2 instances. And a lot of you and a lot of customers are curious about how EC2 instances deliver systems performance. And it makes a lot of sense because a lot of times applications performance depend on the performance of the underlying resources. And then the cost effectiveness of EC2 and the agility it provides depends on our ability to be able to quickly spin them up and shut them down. And so we do that with virtual machines. And in this talk, we're going to talk about how we deliver systems performance through virtualization. So whenever I talk about EC2, I first caveat the entire discussion by saying EC2 is huge. And it's huge not just because we operate at a massive scale, but because there are a lot of different facets to EC2. And you'll notice looking at the agenda that there are a lot of different talks on the aspects of EC2. There's a great talk happening today about the different purchase models that Joshua Bergen's giving, and he'll dive deep with you all on how you can purchase EC2 instance using spot, using reserved instances, using on-demand to optimize your spend. You can learn a lot about the ways that you interact with EC2, the API, the console, the different parameters that you can use to launch EC2 instances. And I kind of relate that to if you want to draw an analogy between an EC2 instance and driving a car, this is getting in the car and turning the ignition. You can also learn about our networking infrastructure, both the physical infrastructure and then our virtual networking capabilities. Those are the VPC capabilities. And in this talk, we're going to learn about the virtual machines themselves. So if you get in the car and you turn the key, this is about driving the car. And more specifically, EC2 instances are sitting on physical hardware in our data centers around the world. On top of that's layered a hypervisor, which manages the virtual machines. And on top of that are the instances themselves. And a little bit about our history. So back in 2006, when we first launched EC2, there was actually one instance, and it was just the instance. And when we came out with more, it became the M1 Small. But it was the M1 Small had 1.7 gigabytes of memory, and it's existed for a long time. You can still go and launch an M1 Small today. But over time, we've dramatically expanded the breadth of our instance offering, and we've done that in a couple of ways. One was by introducing more families of instance types. And a family is a category of instances that's purposed for a particular workload class or workload categories. For example, you'll have storage optimized instances that are good for databases because they offer lots of I/O or lots of disk space. Or you'll have GPU instances which are good for accelerating graphics. And we've also introduced generations within each of those families. And generations are a mechanism for us to deliver differentiating performance within a family, one generation to the next. And so an example of a new generation would be C4 instances. We launched C4 instances in the compute optimized family, and they featured a new custom AWS Intel CPU at 2.9 gigahertz and new instructions. So that's how we've expanded our instance offering over time. And so in this section, we're going to motivate the conversation a little bit up front by talking about how you define system performance, because in order to improve performance, you need to first define it and then know how to monitor it. Then we're going to talk about how, through virtualization, we deliver the different aspects of systems performance, CPU compute performance, memory performance, and I/O performance. And along the way, we'll do quick exposés into instance types that are relevant to each category. So in the compute section, we'll talk about C4 instances, and we'll talk about T2 instances. In the memory section, we'll talk about our recently announced X1 instances. And in the I/O section, we'll talk about I2 instances. And in each, while we want this conversation to be mostly educational and about how virtualization works, we also want you to be able to take away tidbits of information on how to get the most out of your EC2 instance experience. So first, defining performance. Now, servers are hired to do jobs, and what that means to you really depends on your business or personal objectives. but performance is going to be defined differently depending on what those are. And what performance is can be generalized into a couple of different categories. One would be response time. So when you want to do a unit of work, how quickly is it done? Another is throughput. Over a unit of time, how much work can you get done? And consistency of performance often matters a lot. And what these things are more specifically depends on where you are in the application stack. If you're up at the workload level and say you're running a database, response time would be, when you issue a database query, how quickly does it come back? And your throughput could be transactions per second or queries per second. When you go deeper into the application stack, you start looking at things like file system performance and how effective is your file system cache. And then when you go even deeper into the stack, down to the device level, you're considering what's the performance of specific resources, hardware resources, the clock frequency of the CPU, how well it's utilized, disk I/O, network, and memory performance. And so this is an example of some of the performance factors you consider at the resource level, and these are the things that we virtualize and deliver in EC2 instances. So you've got CPU, where what you're considering is the number of sockets, the number of cores, the clock frequency, and the key indicators when you look at your monitoring tools are going to be how well your CPU is utilized, and if it's saturated, is there a run queue length. For memory, there's memory capacity, and when you look at your monitoring tools, you're going to be concerned with, is my memory being completely used, or is there free memory? Is there anonymous paging happening? With network and disk, you'll consider the capabilities of both of those devices. For network, it'll be your packet rate performance, it can be your bandwidth, and then how you're utilizing those two things for a particular instance. And then for disk, it's your input-output operations per second, or your IOPS, and your disk throughput. And the key is to know that any one of these dimensions can be fully utilized and bottleneck your application. In other words, if you're 100% using your CPU, it can't accept any more work, and you won't be able to improve your application's performance, it depends on it, unless you add more CPU horsepower. The same can be said for disk or network I/O, and then also for memory if you end up doing a lot of swapping to disk, for example. And a quick note here is that monitoring tools often operate at coarse-grained time intervals, so you don't necessarily, when you look at something like collect-D charts or other tools that you're using like CloudWatch, you might see CPU utilization up in the 70–80% range. It could still mean that your application is bottlenecked on that resource. It's just the time interval is not granular enough, and once you go down to the second level or the 10-second level, you'll see it more clearly. So to make these notions a little more concrete, what we did is we set up a sample web application. This is, and we applied some load to it. So the setup here is an M4 large instance running a MediaWiki installation, a pretty basic installation. You basically Google MediaWiki and install it, and this is roughly what you get. And we used a client instance using Siege to deliver a request per second rate to that server. And then also on the server, we used collect-D, which is an open source monitoring tool, to record system statistics. We increased the load over time, and I'm going to run through some of those statistics here to show you, where we're finding the bottlenecks. So we first look at memory, and memory looks pretty good. The M4 large has 8 gigabytes of memory, and we're barely using a quarter of it. If you go and check actually the swapping statistics or the anonymous paging statistics, you'll also see that we're not doing any of that. So there's plenty of memory on the system. We looked at disk statistics, and what's hooked up to the M4 large is actually a EBS volume with a healthy amount of IOPS. It's an EBS GP2 volume. And when you look at the number of IOPS that are being driven and the bandwidth that's being driven at this volume, it's really not much. And you conclude pretty quickly that it's not disk bottlenecked. And then we looked at network statistics, and you can see the receive and transmit activity that ramps up over time as we increase the load on the web server. And so that's all as expected. And knowing what we know about the packet rate capability, I mean, this is demanding up to 200 packets per second, well within what the M4 large can handle. And so we know we're not network bottlenecked. And then we went and looked at CPU stats, and here we can see that were actually driving CPU utilization quite high. There were some optimizations that we did on the application, like PHP opscode caching, and we enabled file system caching, but nonetheless, the CPU usage ramped up pretty quickly, and you can understand from this chart that if we wanted to improve our efficiency for this workload, we would use a compute-optimized instance type. And one thing to note about this chart is there are really two predominant kinds of CPU usage. One is user mode, and the other is system or kernel mode. And system calls are used to access the state of the system, such as driving disk I/O or network I/O, and other things like timekeeping and memory mappings. So we'll get into more of that later. But instance selection on EC2 is tantamount to performance tuning. So once you go through this exercise of defining performance, understanding it down to the device level, and actually, ideally or theoretically, you can link resource improvements to improvement in the overall business objective that you're trying to achieve. So if you're driving an e-commerce website and you want to improve the response time of your homepage or a detail page, then you can actually relate improvements in the underlying resources of your web application and database tiers to your business objectives of driving sales. And that kind of tie is difficult, but something that's really important to justifying investment in performance. In EC2, well, in contrast to EC2 or before EC2, a lot of effort was put into determining what kind of server should I buy, because it was going to come in a number of months rather than minutes like in EC2, and it was going to land there and you'd be sort of stuck with it for a while. And so a lot of upfront effort was put in and a lot of risk was taken in sort of picking the right server type, and oftentimes that results in over-provisioning the server. With EC2, you can try an instance type. If it doesn't work, give it right back to us and try something again. So that the agility and performance tuning you have just by changing out your servers and changing out the resources for your application is pretty incredible with EC2, and it sort of changes the way you think about performance tuning. Okay, so we've defined performance. We talked about why it's important. Now, how do we deliver performance in different dimensions with virtualization? So we'll first talk about delivering compute performance. What I referenced earlier in the web application example, when we looked at the CPU utilization charts, was there were two predominant kinds of CPU usage. One was the applications usage in user mode, and the other was kernel mode or the system usage. So the CPU has two protection levels. One, which is used for executing privileged or critical instructions that change the state of the system, and this is the highest protection level, and it's where the kernel executes. And then there's a protection level that's for the application or user mode that executes other instructions. And the reason that this higher protection level exists is to protect the system from processes that want to change the state of the system, protect processes from each other. And so when you think about introducing the idea of virtual machines on a system, you would want the same kind of protections for the virtual machines themselves as you get in a traditional system with a couple of protection levels that the kernel, the protection levels that the kernel uses in order to protect the system from processes. And just to reiterate, the web application example, I ran an strace to understand what system calls were being used, to understand which privileged instructions were being used in that particular example. And what you find is, as you might expect, a web application is opening a bunch of files, just getting a bunch of file system statistics, and reading and writing files, and that's evident from the strace. And if you do this for your application, you'll be able to see which system calls are most heavily used. So before hardware support existed for CPU virtualization, and that hardware support provides the additional protection level that allows a virtual machine manager or hypervisor to intermediate access to critical instructions from each virtual machine. Before that, the virtual machine manager needed a way to trap these critical instructions and to trap the critical and moderate the access to the underlying system. So there are two ways to do that. One was through binary translation, which is a really expensive but effective way of doing it, and that is to scan the instruction stream of every single virtual machine for a privileged instruction and trap and then execute it as it's supposed to be executed. This was a really expensive operation, but it meant that you didn't need to modify the guest operating system's kernel. So the virtual machine guest operating system's kernel, you could run operating systems mostly as they were. But because it was expensive in terms of performance, another approach is using para-virtualization. And para-virtualization offers a simplified device model where these privileged or critical instructions are simply ignored, and the guest kernel has to be told to do something else if it wants to, execute those system calls. And so the privileged instructions were replaced with hypercalls directly to the hypervisor. And this improved performance dramatically over binary translation, but it meant that for every system call that you wanted to do, it required a virtual machine manager intermediation. After Intel introduced hardware virtualization for CPUs, Intel VTX, they created a protection level where below the ring that the kernel would sit in, so that you could, each guest virtual machine could run on the CPU as if it were in a traditional system with very little exception. So you eliminate most hypercalls that are required, virtual machine traps that are required to execute system calls. Now, there are still other devices like network and disk I/O devices that are expensive to emulate. And so there's this concept now of PV-HVM where you try to take the best of both worlds. You use the hardware virtualization from Intel in order to deliver great CPU performance in both user mode and in kernel mode. And then you use para-virtualized drivers opportunistically for network, for example, or for disk I/O, for example, or for timekeeping in order to deliver good performance there. And so that's where you get this concept of PV-HVM. And our version of PV-HVM, where you use the right drivers for the right para-virtualized drivers to deliver performance, and you use the hardware virtualization technologies by Intel, is called our HVM AMIs. And most current generation instance types are HVM only, meaning they only support HVM AMIs, and we do that to offer the best experience on those instance types. So you might have noticed in the web application earlier that the amount of time spent on the CPU running system calls was pretty low. So what's an example of an application type where you have really heavy system call activity? One of those types is when you're actually doing benchmarking, or you're doing debugging, or you're doing tracing, as in JVM tracing, and you're issuing a lot of calls to get time. And so we're going to spend a couple of slides giving examples of how you can most effectively get time in a virtualized environment. So the para-virtualized, each instance has a number of different clock sources that it can use. One of them is a para-virtualized clock source where you query into the hypervisor to get your sense of time. And there are other clock sources like TSC, which are hardware counters in the CPU that you can access directly. Now, when you launch an Amazon Linux AMI, the default clock source is called Zen PV Clock, and we do that because it supports the most hardware configurations. But like we said earlier, if you're doing tons of system calls, that trap to the hypervisors adds up and is quite expensive. And so when you're doing something like JVM tracing or debugging, you're better off enabling TSC as your clock source. And TSC actually doesn't require, it can be accessed from user mode, and is one of the most efficient ways to get time on EC2 instances today. So if you want to use TSC as your clock source, here's a quick command you can use to enable it and changing your grub configuration file in Linux. All right, so we've talked a little bit about how CPUs are virtualized. It's also the job of the hypervisor to ensure that each virtual machine gets an allocated amount of CPUs scheduled. And so this is the part we're going to talk about, how the virtual machine manager, the hypervisor, actually schedules the virtual machines on and off the CPU. And there are really two approaches to that. One is to provide a fixed allocation of CPU, where you have dedicated cores to your virtual machine. There's a direct relationship between your virtual machine vCPUs and physical cores. And that can come in two flavors. One is uncapped, where you really just get the core, and the other is capped, where you get a defined portion of the core. And the other is a variable allocation model, where the virtual machine manager will schedule instances or schedule virtual machines onto the CPU according to some sort of algorithm. It could be a fair share algorithm. It could be a deadline scheduler. And the point there is really just to leverage, to drive up CPU utilization on the host. So if you have to run virtual machine infrastructure on premises, you might consider something like that if you oversubscribe a box and you want to drive up CPU utilization while giving good performance or good latencies to each of the virtual machines. In EC2, we provide fixed allocations of CPU to each of our instance types. And I'll talk a little bit more about how we do that. So C4 instances are designed to provide the best compute performance in EC2. They've got custom Intel processors running at 2.9 gigahertz. Customers choose this instance type when they know they're bottlenecking on CPU and they want to relieve that bottleneck. We provide with C4 instances, dedicated, in the fixed allocation model that I talked about earlier, a dedicated access to the underlying cores. So one of the things that we're able to do when you provide dedicated access to the underlying cores is actually give customers more control over the power states of those cores. And in the C4 8 extra large instance type, we provided P state and C state control. Power states is a way of modifying the frequency of each of those cores and enabling different turbo states. EC2 instances are provided with all-core turbo enabled by default. So when you get a C4 8 extra large, it has all-core turbo enabled by default. But you can actually put most of the cores in a lower power state so that you can drive one or two core turbo at frequencies up to 300 megahertz higher than the base frequency. The one trade-off here is that by taking your cores in and out of sleep states and power states, creates some variability in performance. And if that's not something that your workload can tolerate, then you can instead lock your cores to a particular power state. And in a particular scenario where this is important is when you're using lots of AVX2 instructions. So you've got an operation that's parallelizable, and you can leverage Intel's AVX2 in order to get significantly higher performance on C4 instance types. It's a very power-hungry instruction, though, so when you run it, the CPU automatically puts itself into a lower power state. And if you want to prevent that change in power state from happening because you care about the latency of that, then you can go ahead and lock your C4 8 extra large cores in a lower power state that's suitable for AVX2. So T2 instances are designed to provide a low-cost, high-performance experience for applications that don't need CPU consistently or often, but when they do, they benefit from having access to the entire core. This is a pretty cool instance type, I think, because what we observed was a common pattern that whether customers realized it or not, it turned out that many workloads do not fully utilize their CPU. And so we challenged ourselves to find a way to offer customers lower prices and give them a consistent compute experience. And the way that we ended up doing that was coming up with this concept of CPU credits in order to enforce a fixed allocation of CPU that was less than the full core. And the way we did that, let me tell you a little bit about how credits work. So you can think about each T2 instance as having a credit bucket, and as long as there's a positive balance in that credit bucket, it has access to the underlying cores as if you were running like a C4, for example. You've got the full uncapped access to the core. So we call that full core performance, as long as you've got a positive credit balance. So how do you get a positive credit balance? Well, credits are earned continuously down to the millisecond level for these instances, and you're always accumulating a balance. At the same time, you could be spending that balance if you're running on the CPU. So an instance consumes credits when active, and it earns credits at a steady rate all the time. So that the way you find out if your workload is suitable for a T2 instance is actually through a couple of CloudWatch metrics we provided in order to give more insight into these credit bucket balances. And what I like to tell customers is that you should just try T2 instances and run your application. If it works, you'll notice that you maintain a positive credit balance all the time, and you don't see that you don't see it being capped at all. Now, when you run out of a credit balance, what happens is we enforce the average. We enforce the baseline performance by capping the underlying CPU. And so when that happens, it's an indicator that that particular T2 instance is not an appropriate fit for that workload, and you should consider either a larger T2 size or another instance type that offers more CPU. But you can determine all that by looking at our CloudWatch metrics for the CPU credit balance. So monitoring CPU performance in the guest, in particularly with T2 instances, is interesting because of the question of what happens if the underlying CPU is capped. So if you're running a T2 instance and you run out of a credit balance because it's not the right fit for the workload, and I monitor your CPU in the guest, I might see some strange things. And so what happens to my statistics we reviewed earlier, user time, system time, wait IO, in that event? And what tends to show up is steal time. And I wanted to call this out because it's often misinterpreted as meaning that the time that my instance deserves or is entitled to is being taken by something else. And really, in the case of T2, what it should be described as involuntarily scheduled off of the CPU because of the definition of the instance type. So again, tip is to leverage the CloudWatch metrics to understand if your credit balance is full or if it's empty. And you can also see an accurate representation of CPU utilization through CloudWatch. Okay, so that was how we deliver compute performance. Now, how do we deliver memory performance in virtual machines? Why do we care about that? Well, some workloads require lots and lots of memory. And last reInvent, we announced X1 instances, which is going to be our largest memory instance with up to 2 terabytes of DRAM. It's also going to have a quad socket system with Intel E7 CPUs. And so you'll start asking questions about memory locality and how you optimize workload performance when you've got 4 CPUs, memory on each socket, and the potential for a process to run on one CPU socket and access memory on another CPU socket. So we'll first talk about how virtual machine memory works, and then a little bit about non-uniform memory access and how you can take advantage of kernel optimizations so that you don't have to be aware of Numa in your applications and you get the performance of some Numa balancing. So the way to understand how virtual machine memory works is to first understand how it works in non-virtualized systems. And the concept of virtual memory already exists as it relates to processes. And so in a traditional system, you have 2 address spaces. One is a virtual address space, which represents the processes view of virtual memory, processes view of memory. And then you have a physical address space, which represents the actual physical memory on the system. And it's the job of the operating system to map virtual memory to physical memory. The reason for this abstraction is A, to protect one process from another, so one process can't stamp on another process's memory. It also provides the operating system the opportunity to really efficiently utilize the system's memory resources, and it allows the operating system to page memory to disk, so that it gives you more room for more processes. And the way that works is the operating system uses something in hardware called a memory management unit. Memory management unit is a decoder that translates virtual addresses to physical addresses. Memory management unit also has a cache called a transaction look-aside buffer, which is smaller in capacity but can do memory translations super fast. So let me walk through really quickly how this works in a traditional system. So there's a request for a memory mapping. A virtual address first looks at the TLB, and if the TLB has it, it's returned back to the operating system. If the TLB doesn't have the mapping, it then queries a page table, which resides in main memory but has the mappings from virtual to physical memory. And if the mapping does not exist, a page fault happens, And the operating system has to figure out what to do with that page fault and inevitably put the mapping back into the MMU, which then gets loaded into the TLB and the translation occurs. Now this is done at the process level, so if there's a context switch, in other words, another process starts running on the CPU, then the TLB gets flushed and a new page table is loaded for that particular process. And again, that's to ensure that no process has access to another process's virtual memory. Now, some processors, TLB flushes, TLBs, like I said, the mapping performance of a TLB is super fast. So when you flush the TLB and you restart the cache, it comes with a performance penalty. And one way to avoid that is to use address space identifiers. And some processors use address space identifiers so that when you do a process context switch, you don't have to flush the TLB. So that's how it works before you layer on virtual machines. When you layer on virtual machines, what you're basically doing is you're creating another level of indirection. You're reinventing some of the same problems that you were trying to solve with process memory virtualization. And so when you think back to the way the hardware works, what you would really like is a second layer of translation tables so that the virtual address space can be translated to the virtual machine's physical address space, which is not actually physical in a virtual machine world, which is then translated into the machine's address space, which is the physical memory address. Before hardware support for that, the virtual machine manager had to do it on its own, and it did it through something called shadow page tables. And the hypervisor maintains shadow page tables, which are essentially the maps between a guest virtual machine's virtual memory address space and the machine's physical memory address space. This got swapped into the MMU, loaded into the MMU every time a virtual machine was scheduled onto the CPU and had a process scheduled onto the CPU. And the challenge for the virtual machine manager was to make sure that it kept in sync its view of the virtual to machine mappings, along with the guest's view of its guest to virtual to physical mappings. So we'll talk a little bit about how that worked and why that was inefficient. So following a similar flow to what we had before, the mapping is requested. If it exists in the TLB, which has virtual to machine mappings, it'll succeed and the translation will be provided. If not, it looks into the page table of virtual to machine mappings. And if it's not there, instead of what would normally occur, a page fault happens, which is trapped by the virtual machine manager and then acted upon. And it basically walks through its copies of the guest page table, guest virtual to guest physical memory, and then its own versions of the guest physical to machine memory to then load them into the MMU and again into the TLB. This is a highly inefficient process because it involved tons of virtual machine intervention and traps. And it also required a lot of memory overhead because it had to maintain copies of the guest's virtual to physical page tables. So what happened is Intel created something called extended page tables, which gives you the world that I described earlier that you would like, the ability to walk in hardware from a guest virtual memory address space to a guest physical address space through to machine address space. And with virtual machine identifiers, there was no need to flush the TLB on a VM or hypervisor context switch. And this is, again, just a quick diagram of how that would work. You miss the TLB, you walk through the guest virtual to guest physical page table, and then the guest physical to machine physical page table to get the address translation. So I talked earlier about Numa and the performance impact of non-uniform memory accesses if you're accessing memory that exists on a remote socket. And so like I said with X1 is going to have a quad socket system, and there's an opportunity for a process running on one of the CPU sockets to then access memory on another CPU socket. The local memory accesses, so a process running on one CPU core accessing local memory, is substantially faster than those remote memory accesses. The thing that connects the CPUs is what's called Intel QPI, Quick Path Interconnect, which is a high bandwidth, high-speed interconnect, but not as fast as what you would get with local memory. And so the tip here is to make sure that the kernel that you're using supports Numa balancing. In Linux, since version 3.13 of the Linux kernel, and in Windows, really since early versions of Server 2003, and particularly you'll get it with 2008 and 2012, there is automatic Numa balancing, so a number of algorithms that are used to create locality between your processes and the memory that's been allocated to those processes. And as long as you're using these kernels, your applications can benefit from those algorithms without being themselves needing to be Numa aware. Okay, so we've talked about CPU and memory. Now we're going to talk about delivering I/O performance. So how do you get super fast disk or network performance in an EC2 instance? Well, the way it works is the virtual machine manager needs to schedule access to shared physical devices across multiple virtual machines. And the way that that's done in Xen is with a split driver model. And another way it can be done is through direct device pass-through. So we'll talk about both of those things. But first, the split driver model. I'll tell you, this chart will show you a little bit more about, well, the chart coming up will tell you a little bit more what it means. But why do we care about this split driver model? It's because when you're doing lots and lots and lots of I/O, any overheads in the process of doing I/O in a virtual machine world are going to add up, and you'll notice them. So I2 is an example of an instance type that drives an insane amount of I/O. You can, with the largest size, the I2 8 extra large, drive 365,000 IOPS. And so any overheads in the process of delivering I/O, delivering reads or writes, is going to be noticeable. So here's the split driver model and how it works. So within a system, you'll have what's called a driver domain. And the driver domain will house the physical device drivers for the devices you're trying to schedule across multiple virtual machines. And so this could be disk device drivers, or it could be network device drivers. And each guest will have what's called a front-end driver that communicates through shared memory to the driver domain's back-end driver, and the driver domain then schedules requests to the network devices or disk devices. There are really three components to the delivery of I/O using the split driver model. The first is a communication ring buffer for issuing commands. So the guest virtual machine will say, I would like to do a read, or I would like to do a write, and here's the memory that I'd like to use for that, and here's where I want it to go. And it'll write those desired commands to the communication ring buffer. And then the second part of the architecture is an event channel signaling that there's something in the command ring buffer to the driver domain. Once a signal is gotten, the driver domain knows what to do with it. And the data is communicated through shared memory pages. So I know I want to do a read. How do I get the data from the driver domain over to the guest domain? And that's through shared memory pages. And what actually has to happen is the guest needs to grant memory from its address space to the driver domain, so the driver can then input data into those memory addresses. So pre 3.8.0 kernels, here's what happened in the process of granting memory. Granting memory requires hypercalls to the hypervisor. And so like we've seen in the past with whether it's memory mapping or system calls, hypercalls are expensive and they add up. But what would happen is the instance domain would issue a hypercall to grant shared pages to the driver domain. It would then write to the ring buffer, including the commands it would like to do, plus the grant references. It would signal event. The driver domain would then go look at the command buffer, get the commands, get the grant references, map the grants, read or write to those grants, and then unmap them. And it turned out that this happened for every single I/O request. And so if you're using I2 instances, for example, and you're trying to drive 365,000 IOPS, but you're not using a post 3.8.0 kernel, that's actually pretty hard to achieve. So in order to solve this problem, in 3.8.0 and beyond kernels, what happened was called persistent grants. And persistent grants basically says, let me pre-grant access to shared memory pages between the driver domain and the instance domain. And instead of doing a grant every time, what happens is we'll just copy data to those pre-granted pages and do our I/O. And this has dramatically reduced the number of hypercalls required in the process of doing I/O and dramatically improve performance for any I/O operation. So you're talking about, again, disk I/O and network I/O. So the tip is to use 3.8.0 or greater kernels, and that's Amazon Linux 13.09 or later, Ubuntu 14.04 or later, and RHEL 7 or later. So the other way to deliver I/O is through direct device pass-through, and the idea there is asking, why do we have to go through a driver domain? Why can't we just take a PCI device and pass it directly through to an instance and give the instance exclusive access to its functionality? And you can do that with single root I/O virtualization. You eliminate the need for a driver domain because you're able to pass through virtual PCI functions directly to an instance and get awesome network performance. Requires a specialized driver within the instance, and you actually need to tell EC2 that that's the device you want presented to your instance. And you tell EC2 that that's the device you want presented to your instance through an OMI flag or an instance flag. So after enhanced networking, you've completely disintermediated the driver domain. The guest application, in the case of networking, creates a socket, accesses the NIC driver in the guest OS, which then talks directly to the SRIOV network device, which is our enhanced networking device, and goes out to the network. And with this, you actually get the highest packets per second rate you can get. You can get the lowest variance and latency, and just a reminder that the instance OS must support it. So that was a quick run through all the different ways that system performance is virtualized, and why, how we're able to basically deliver awesome performance in EC2 while also providing agility and the ability to spin up and down instances on demand. Quick summary, just remember that choosing an instance is not a one and done decision. You can give instances back, and so a lot of performance tuning is experimenting with different instance types, monitoring resource utilization, and then picking the instance type that gives you the most efficiency for what you're trying to do. And the virtualization themes to date have been one of driving bare metal performance. And we've seen that in many scenarios, bare metal performance already exists. If your CPU is running in user mode, it's running directly on the CPU. For most, with hardware virtualization, in kernel mode, the same thing. With enhanced networking and direct device pass-through, we're also disintermediating driver domains and giving more direct access to hardware. And so this is just a quick recap. To get the most out of your EC2 experience, remember to use PV HVM OMIs. For timekeeping, as an example of a system call heavy application, use TSC. With our high compute instance types, we provide direct access to cores. And by doing so, we give you more control. You get access to controlling P states and C states with a C4 8 extra large. Consider using T2. Try it out. See if the fixed allocations of CPU we provide through the credit system there work for your application. You could save a lot of money, and you can use CloudWatch metrics to determine if they're a good fit. Use kernels that have automatic Numa balancing. Use kernels that have persistent grants enabled for I/O performance. And make sure you're using enhanced networking for the best, highest performance networking experience. So for more information, a lot of this, minus some of the gory details that we went through, is available on the EC2 website and the EC2 docs. And come see us in the Expo Hall developer chat to learn more. So thank you very much.